Kai will talk about multiphase lattice Boltzmann methods towards a unified formulation. Kai, you have 40 minutes in total, including questions, and I will let you know after roughly 30 minutes so that you have about 10 minutes to conclude. Okay?
Thank you very much, Tim, for your kind introduction. And many thanks for the organizers. Many thanks to the organizers for the invitation. Now let me see how I can turn it down. Okay, let's see. Okay, do you see my screen?
Not yet. I can see you.
Okay. Isn't that sharing?
If you at the bottom left, bottom right, sorry, there's a button that says Present Now.
Yes, I press that, yes.
And then you have to select the window that you want to share.
Select the window, yeah, okay. Okay. Entire window, entire screen.
You can choose entire screen or a particular application, like PowerPoint or PDF. Ah, something is happening.
Okay.
Yeah, we can see it now.
Okay. So I hope you can see my PPT now, yeah?
Yes.
Okay. Thank you very much. So I slightly changed the title to a unified framework, which I find it easier to explain. So the talk will consist of these 5 parts. The focus, of course, is on multiphase phenomenon, and this the various phenomenon happen in nature and especially in industrial applications, including nuclear power plants, fuel cells, and of course engines. So there are various methods to deal with multiphase flow. They are color-graded LBN, phase field, free energy. They are all developed still actively, but my focus will be on the pseudopotential LBN for multiphase flow. And this started with a sentience model with a density-based pseudo potential function with the interaction force written in terms of this pseudo potential. And they are both single component and multi-component models. So the reason why I focus on this is because of its various advantages, including the fact that it allows the equation of state of your choice, and also allows non-zero surface tension, phase change automatically with your pseudo-potential function. And of course, it also allows the interface to arise, deform, merge. But above all, it's because of its simplicity and numerical efficiency. The various LBN models for multiphase flow have been developed almost in parallel, and they all started with various problems, but these problems are gradually solved. So among these, we can see the free energy model and the pseudo-potential model are capable of dealing with phase change, and that's also one of the main reasons we have chosen this to focus on. Now, in the original model or the basic model, there is a thermodynamic inconsistency, and this is the inconsistency between the mechanical stability condition and the thermodynamic theory. And also the density ratio is achievable is about 10, and surface tension is not actually independently set. And also there are various spurious currents around the interface. So the work for the past, let's say, 20 years or more, 25 years actually, has been to actually overcome these difficulties and make the model much more powerful and accurate. So firstly, we can look at the various force intents we have used. Of course, these force intents are developed for single phase flow at in most cases, and then they are applied to multi-phase flow. Here is a list, but not exhaustive. There are many others, but we can actually put them in a uniformed way and look at the differences. The question is that which force intent to choose? The answer is that none of this is good enough. Now, the reason for that is, first of all, we need to satisfy the mechanical stability condition, which means basically the equilibrium pressure, normal pressure should be to interface. Pressure normal to the interface should be equal to the static pressure in the bulk. And also we need to satisfy the Maxwell construction, which gives the thermodynamic consistency. The only way you can reconcile these two is when you set your pseudopotential function like this. But this has various limitations. In most cases, we would like to have a more general equations of state and allow the phase change. So inherently, we cannot meet these two conditions simultaneously. One of the first, one of our initial efforts was to actually change, slightly modify the Gore forcing scheme by introducing a modified velocity with the tau as an adjustable constant. And in this way, we can actually derive the mechanical stability condition, and by changing the parameter sigma, we are able to change the mechanical stability condition so that the thermodynamic consistency is approximately achieved. And this increases the density range achievable by the pseudopotential model to several hundreds. And there are differences in terms of how the models would perform. For example, with just the slight improvement I've just described, we're able to actually simulate the stationary point droplet much more accurately, while we can see the original Sanchin scheme, the EDM scheme, the Goose scheme, they all introduce some inaccuracies. Okay. So the okay, wait a second. This is okay. This is repeated. So improved version, further improved version, which is also incorporated in the MRT framework, reads like this. Basically, in the from the original model, we introduced these two terms, and in a very similar fashion, and we are able to actually extend the density ratio to about 1,000 or slightly more. This were demonstrated in various calculations, including stationary droplets or droplet evaporation, and also droplet impingement, and at reasonably high Reynolds number and also density ratio. However, those are not actually realistic parameters yet, because realistically, we are talking about density ratios about 1,000 or several thousands, and Reynolds number much higher than that. And so we tend to a slightly more complicated formulation, and the idea comes from the first, the work done by Alexander Wagner many years ago, 2006, which noticed that the second order Chapman-Enskog expansion is often insufficient to actually identify the error tense in the pressure tensor, and of course in the final recovered macroscopic governing equations and properties. So and Daniel and myself, we start to derive the to conduct the third order analysis of the LBN, and this is the basically it's Tyler expansion, but carried out to a higher order, and from this we can find the recovered Navier-Stokes equations with additional terms, and also the pressure tensor with additional terms. And of course, this additional terms cause the problems in simulating the high density ratios and other parameters. And the idea is to actually compensate for these errors. So let's look at the with the third order analysis, we can find that the mechanical stability condition is written as this, and the sigma now is a much more complex function, and we can also identify that the for example, the sensing model is this parameter gamma is dependent on the relaxation time, which also means the mechanical stability conditions depend on the relaxation time. So as you change the relaxation time, of course, your density, your stability, and also the thermodynamic consistency are changed, and that really reveals the problems of this model. And we can also say that the Gauss Forsen-10 has this parameter, and when you substitute this into this, you will say that it only satisfies the Maxwell reconstruction under limited conditions. The same applies to EDM. So previously, people have done extensive calculations comparing these three models, and they pointed out which model is better than another. In fact, all those were actually coincidental rather than theoretical. So we found that the in fact all these models will not actually be able to simulate high density ratios. So the with this finding, we were able to actually construct an approximate model to actually achieve approximate thermodynamic consistency by selecting the epsilon according to the the equation of states of our choice. And in fact, with the various available equation of states, the performance will be slightly different, or sometimes dramatically different, and this is all related to the thermodynamic inconsistency as a result. So with this, we're able to actually construct a modified Fosson-10, which is able to adjust the various parameters to satisfy, first of all, the approximately the thermodynamic consistency through gamma or epsilon. We can also adjust the surface tension independently by changing kappa. Finally, we're able to actually adjust interface width through the a good combination of these parameters. And this turned out to be very useful in terms of extending the density ratios we can achieve. For example, we are able to actually prove that for the GAU and EDM schemes, the Fosson schemes, even if they change the interface width, the performance will not improve. But for the modified model, we are able to actually we can say that, you know, if we change the well, firstly, ensure approximate thermodynamic consistency, and also through interface refinements, we are able to actually reach density ratio, you know, over meanings. So in a way, we can arbitrarily set density ratios. Arbitrarily high density ratios can be achieved with this Fosson-10. And equally, we show that the surface tension can be adjusted independently and over a range, a wide range. And this is, of course, under a very high density ratio. And we also see that the spurious velocities or non-isotropic can be reduced or by orders of magnitude if we slightly increase the width, or actually increase the grid resolution or lattice resolution near the interface. Okay, so those were the efforts to achieve, let's say, a realistic density ratio. But there are also other issues like, you know, surface tension adjustment. For example, Shragaglia has proposed a multi-range potential LBN to deal with surface tension independence or dependence on the density ratio with limited success. So we actually worked on this and introduced additional term in the Fosson-10 under a MRT scheme, and we're able to actually also achieve surface tension tuning independent of the density ratio using different formulation. In the end, we can demonstrate that with formulation, which is in fact very similar to the Lattice, Brown and Law Fosson-10, we're able to actually vary the surface tension over a wide range, and simulate both the dynamic process and the stationary process of multiphase flow. Another issue, of course, is the contact angles, and we have some various schemes to deal with contact angles on flat plates, but many multiphase flow happen on curved boundaries. There are basically three methods to deal with this. The first method is called solid fluid interaction scheme, which basically divides the lattice into solid phase and fluid phase, and specify density for the virtual density for the for the solid phase as well. So another method is called the virtual density scheme, which has been applied with some success. And there's also a geometric formulation, which can be extended to the curved formulation. We made a small improvement to the scheme by introducing a variable solid phase density into the scheme. So what happens? So firstly, we see that for the virtual density scheme, we can see that the here is a drop on the circle or sphere, and we can see that the the contact angle is approximately right, but we can see the liquid is all around this solid circle, which is which basically means there is fluid leaking between the solid phase and fluid phase. So with the slightly improved scheme, we are able to actually say that it is actually this problem can be overcome. Okay, so we can see from these lower graphs there's no problems around the circle, and we can also see that the scheme reduces the spurious currents around this interface, especially the contact angle. Okay, so this is improved scheme. Finally, we can see the dynamic effects. We can see the first one is a virtual density scheme, the original one. Second one is a geometric formulation, which is okay, and also with an improved scheme, we can also calculate this phenomenon quite accurately, while the first one gets the phenomenon completely wrong. Okay, so another topic I want to briefly talk about is cascaded LBN, and the idea comes from Geyer's work, which uses central moments instead of the raw moments in analogy to the MRT scheme. And so here are the top one is the raw moments, the second one is the central moments. So in the literature, there's a mixed use. Sometimes we say it's cascaded LBN, sometimes it's a central moment based LBN, but in any case, it's shortened to say LBN. So probably Daniel is the first one to apply these concepts to multiphase flow in around 2014. And we did some simple tests in shear layers. We can say the BJK isn't performing well, and the cascaded and MRT can simulate this well. But if we push the Reynolds number higher and velocity higher, then we can say the cascaded or say LBN has better stability than MRT. under identical conditions. So we apply this to various phenomena, including those experimental studies conducted at Princeton University. We are able to actually simulate the various regimes of micro droplet collisions. Applying the same the forcing scheme we developed earlier, we're able to achieve very high density ratio and surface tension independence. And here is an example where we apply this to droplet collision case with high density and high Rayleigh number as well as large Weber number. And we got good results in comparison with experiments. This method is the cascaded LBM was also applied to a spray case, and in this case, there's a good comparison between MRT and say LBM. Actually, they can all achieve very high Rayleigh number. In this CLB case, we achieve Rayleigh number around the meaning, and the maximum Weber number, 10 to the power of 4. And also, we notice that the spurious velocity from CLBM is much better than MRT. So that is a very good, in a way, comparison conducted by a group in Japan using the models we have developed. So here I'll talk a little bit about the, what I call the unified framework. So we see the SRT and MRT operator, and we have also seen the cascaded LB operator. In general, if we move from left to right, we increase the stability, accuracy, and of course, complexity. The point is that, can we actually unify all these three? It is possible, and if we define the various matrices, we are able actually to write all three operators in a unified way. So here, M is a transformation matrix which transform from raw moments to center moments. Transform F into raw moments, and N shifts the raw moments to center moments, and S is relaxation matrix. And when N and S are here we see trivial is a unit and a scalar, we are able to actually okay, when these are general, we can say we have the cascaded operator. When the shift matrix is unity, we get the MRT scheme, and when all the relaxation time is equal, then we get the SRT operator. So in this way,
Kai, 10 more minutes.
Sure. In this way, we are able to actually unify the three operators. And here are samples of those matrices. And so, why do we do this? The point is that firstly, for the mathematical clarity, we are able to put everything into a uniform formulation, and we can also write the code in a uniformed way. And we clarify the relationship. Once we've done that, we're able to actually swap or exchange the various models and boundaries between the MRT and say cascaded LBM. And in this way, we are able to actually easily make use of existing MRT schemes and construct say LBM. And finally, we are able to actually construct a non-orthogonal skins for both MRT and say LBN. So so here is example of how we actually use the GMRT framework to construct the Forsen skins based on the He Forsen scheme. We're able to actually demonstrate it performs. Here is an example of how the difference between MRT and here is another development in terms of making the the basis non-orthogonal. In the original MRT and say LBN, we have the orthogonal condition, but we don't have to do that. Only we have the linearly independent basis vectors. In this way, we can significantly reduce the matrix size and simplify the elements. So there is an original with full matrix, and we can get non-orthogonal with lots of zero elements, which in the end significantly reduce the computational costs and all this. And we can actually demonstrate that the non-orthogonal skin can recover the Navier-Stokes equations. Some of the tests to show that indeed the non-orthogonal skins have higher computational efficiency and similar performance, as well as better portabilities. Lastly, I want to mention about the fact most of the models, MRT or say MT, at an initial stage were basically selecting the models based on experience and various basic principles. But in a recent work, Ian Collin has applied the entropic conditions to MRT skin with success. I believe this entropic condition can be incorporated into what we call the GMRT, or the generalized MRT skin. So here is my rough idea to put everything together, and that is we can we have all these elements to form a more or less unified framework. We have the GMRT unified operator. We have improved the Forsen skins, which increase the range of parameters we can simulate for multiphase flow to realistic conditions, improve the boundary conditions, and we can also apply the entropic condition to better achieve better convergence and selection of model constants. We can also use adaptive meshing near the interface. And another successful approach is to basically increase the lattice size, which has been demonstrated by many people. So I will not talk about it here. So here I will just show you some applications now, and here we apply the GMRT skin to simulate droplet impingement on a semi-cylindrical ridge, and we achieve basically good agreement between simulation and experiments. Here we apply the method to a droplet impinged on a perforated plate, and we see how the droplets actually pass through this small hole, and we see three regimes, different regimes under different physical parameters, and we can actually put them into a regime diagram, and using theoretical analysis we can define the theoretical boundaries. There's another example, droplet impingement on the screen mesh. And again, we can actually do some analytical work to to find out the various mechanisms based on the energy and force interactions. Here is one example of multiphase flow simulation in fuel cell gas diffusion air. And in this case, we see how the droplets submerge into the gas diffusion air. And we have also simulated how a droplet can emerge from this. And here is an example, which is actually an extension of the multiphase simulation into multiphase thermal multiphase LBN, and we simulate the boiling case, pool boiling case under various regimes, and reproduce all the regimes observed in experiments. Another simulation is convective, a forced convection boiling over a cylinder, and again we are able to identify different regimes through this. Here is a frosting case in which droplets actually freeze, become ice, and here is convection frosting. So also we can extend the multiphase to multiphase with different components and study the instabilities. And finally, we can also look at the reactive case. Okay, observe instabilities in some cases and stable cases in others. So how do LBN compare with other methods for multiphase flow? Now this work has been done by others. They have found that the LBN basically is about an order of magnitude faster and produces 1 to 3 orders of magnitude lower spurious velocities compared with VOF, and compared with the volume of fluid or combined finite element. LBN is also seen to be able to produce about 10 times faster solution, and in some cases there is qualitative difference. For example, the LBN can actually simulate these droplets split into 2 droplets in this case, while the VOF or the traditional methods, microscopic methods, cannot simulate the droplet split. Okay, a couple of years ago, or many years ago now, my student Daniel went to work for a company called XFlow. I wasn't sure why, and in the end I found out what they're doing is some really great applications of LBN simulation. I believe this is done by, say, LBN. Okay, so this is a case of a complex engineering type of multiphase flow, and this is offshore wind turbine. So you have the ocean flow, you have the aerodynamics, you have rotating boundaries, and all this. So this represents a highly complex cases. Another case is a launch of a ship to study the instabilities of the ship. So we can say, this involves complex multiphase flow and also fluids and structure interactions. So those are the results I want to present, and finally I want to just to draw some brief conclusions. So we can see a unified formulation is possible. We are working towards that goal. Various improvements have been made to the forcing scheme to achieve high density ratios, large Weber number, realistic contact angles or boundary conditions, and above all reduce the spurious currents. And now thermodynamic inconsistency is an inherent part of the pseudopotential LBM model. We are able to actually correct this to a large extent, but it's not 100%. In terms of the applications, we have some both, canonical problems and engineering problems can be now solved by multiphase LBM methods. As Tim mentioned, we work within the UK consortia on mesoscale engineering sciences, which involve 21 UK institutions and many overseas institutions. Finally, I want to thank many people who I have had inspiration from and collaborated with. Thank you very much for your attention.
Thank you, Kai. That was a very comprehensive overview of what the Shenzhen method can do these days, so thank you for that. In the interest of time, I would say we have maybe the opportunity for one question or comment, and after that I would like to wrap up the session for lunch break with your favorite Italian food at home. We have time for one question. If there is no question or comment,
may I ask a question?
Okay, please.
So now I have to. So, Kai, thank you very much for this very nice overview. Obviously, many people worked on these issues for many years. Results in the end are quite impressive. But I wanted to ask a little bit into the perspective. So you're mentioning very much, quite often, and that's true, the thermodynamic consistency or inconsistency rather. And my question is, so these models which are developed, so they're using some input from thermodynamics, basically the equation of state, and sometimes also the energy somehow in a rather truncated way. But from the physical standpoint, so the equations of state, let's say, wonderful. So they are valid not just in the coexistence domain, but much wider. ET diagram is very big, so there are regions out of that. So my question is rather, any of these models can or are used in wider range of parameters, temperatures, pressures, let's say. So including supercritical maybe, things like that. So phase transition, so critical point. So
okay,
I think you're the right person to be asked, because
no,
obviously know the landscape of the model.
Yeah, Ilya, thank you very much for the question. Now we have used this equation of state to basically achieve very high density ratios. That's our focus, our work. We have not actually studied the supercritical multiphase flow, and I have seen your work on day one, Monday, which is excellent, and that's something that we should consider in future. Really.
No, I mean this. I just a small explanation. So our work currently being stuck in the journal with a referee who is in 3 reviews asking us to compare this to existing Lattice Boltzmann, which would simulate your supercritical states. I myself have not seen, but maybe you have seen. Somebody have seen.
No, I haven't.
just to be sure that we think we we did. But so there is a way to go, essentially.
Yeah, sure. I mean, you can. I'm sure you can. I'm sure you can. Yes. Just we haven't tried it. Yeah.
Okay, thank you.
Thank you. Yeah, I really wish I were in Italy for the conference. But finally, we have to settle down with, as Tim said, food at home and the sunshine at home. Thank you.
Thank you very much, Kai. Thanks again. All right. We are having a lunch break now, and I believe we meet again in about 1 hour and 10